to find the highest electronic level through the MS. I forgot what it's called. Bust out to the quantum numbers. So I'll start off with an example of um let's say, let me just make this bigger. Um 1s2, 2s2, 2p6, 3s2, and 3p6. Now, in order to get the HEL, we have to find the last number. So this is the last number, right? 3p6. So if 3p6 is the last number, we have to find the coefficient, which is 3. So HEL is equal to 3. But there's also one more thing. HEL in the period, or the P is both the same. So period is equal to 3, same too. Now, how do we get the valence electron? It's 6. The valence electron is 6. Whatever is the exponent or valence electron of P, that's the valence electron. So now we have uh-oh. Now now that we have what the hell did it? So now we got HL3 PN3. Now we have the highest electronic level and the period number. The valence electron, or VE minus, is equal to 6 due to it being the exponent, or the electron level of P. And since you also have to find the group number, GN, which I call group number for short, is the same as the valence electron. So it's 6. So this is how you find the thing. The highest electronic level. Keep in mind, the highest electronic level is the same as the period. The valence electron is the same as the group number, and they're both very easy to find. Now here we have is the quantum numbers. So to find n, it's how do I explain this? Basically, to find n, we have to get the last term. Okay, so the last term is 3p6, right? 3p6. So the last term, n is 3, because it's looking for the coefficient. So n is equal to 3. That's the first quantum number down. Now we have to do L. Now, to get L, it's pretty easy. I'm gonna get another example. So there's a rule when you're finding L. S is equal to 0, P is equal to 1, D D is equal to 2, F is equal to 3. Now, the last term is 3p6. Alright? The last term is 3p6. P, specifically P. So if you look over here, P is equal to 1. So L is equal to 1. Why is it like that? So L is equal to 1. Now that we know that L is, what the hell is it like this? What did they do? Undo. So now we know that L is equal to 1. Now here's the more complicated things. God damn it. Here's the more complicated things. We got ML and MS. ML is um magnetic, how would you call that again? Magnetic number or something? I forgot. And this one, MS, is but magnetic spin or something. I don't clearly remember. So this is what you call quantum numbers. NL and ML, N and L, and ML and MS. This is the the part of the electronic configuration. This is the quantum numbers that mom made us find. So how do we find M? Now we already know the given of N and L, but it's gonna be way different than that. Now, when you do the like the box, right? Like the box, up, down, up, down. For example, since I don't know how to type that, up and down. Let's say up and down. Oh, it will type up, up, down. Yeah. So if it's one box, it's it's equal to S, because S can only fit two arrows, which is up and down. Now we know that, of course, like that, right? We did the electronic configuration. So what does this have to do? All right. So if you count here, there's only one box. It's zero, right? No, okay. Wait, it's really hard to explain, but I'll put it like this. Suppose that there's three boxes: up, down, and up, down. Now, in order to find ML, we put it like this. Let me do this. This one is positive one, right? Right? Because if this one is one, I'm just gonna type it in immediately, like the pattern itself. This one is zero, and this one is negative one. Do you see a pattern over here? The pattern is that it keeps on decreasing. Now, what if there's five boxes? All right, let's say five. For example, now we know that this is P because P has three boxes. So, for example, P, like example, up, down. This is just an example, and up, down. Whatever happens here is that it gets added by one. So this one is going to become positive two, and this one is going to become negative two. Basically, every time you increase, you add by one in the left side, and you add by one in the negative one in the other side. For example, over here. I'm gonna connect this over here. It won't work over here, right? Over here. Now we see that this one is zero. This one's both the same, but we added one in both left and right, which is negative one and one. So this one here becomes one, and this one here negative one. If we do D, for example, D, if it's like two 2s2, for example, 2s2, we're going to 2s2, which is going to become 0. But if you do 2p6, there's three boxes, so we're going to add both we're going to add one both. Okay, now we understand, right? We understand how that works exactly. So I'm going to move to a new page, and I'm going to explain how how we can use that to find the thing. Okay. Okay, for example, here we got 3p6. So the given is 3p6, right? 3p6. Excuse me. Um, what basically happens over here, let me just, what happens here is that there's p. P is equal to 6. So 6 boxes. Gonna put up, down, up, down, up, down. Now, you see a pattern, right? Like what I said earlier. This one's gonna become 0, 1, and negative 1. The rule m to find ml is that whatever is the last one, we find the arrows, like the amount of arrows, and whatever it is, like if it lands on negative 2, then it's negative 2. For example, right? We got negative 3p5. Now, this is incomplete, right? So what do? Up, up, up. So that's three arrows going up. But it's only five. It's not six, unlike this, which is complete. So this one's gonna come down, down. You see this? It's down. It reaches down over here. So, since we know that this is specifically um negative, I think. Two, two, four, five, six. Holy I forgot. Wait, I'm gonna search up my. Yeah, I'm gonna search up. For example, three, three, six, five. Ah, okay. So whatever it stops, like one, two, three, four, five. So over here it's five. It's gonna become negative one because if you do here, one, two, three, four. Okay, I think I understand it. Oh my god, that's a lot. So here's how it goes. This one is positive two. This one, right? Positive two, but one. This is one, right? One, zero, negative one, negative two. One, two, and positive one. So this one is negative two, and this one is negative two. But this one, if you compute this, no, like over here, there, I would just there. Now this one, which is all the way here, which is one. Now do you see the pattern, guys? Do you see the pattern? This one is positive two, positive one, zero, negative one, negative two, and oh wait, what the fuck? Oh my god. Okay, so I just double check my explanation was correct. I was just trying to find a way to explain it better. So this one goes up, right? Right? Up, up, down, up. I meant up. So this one is equal to zero. The third up is equal to zero, right? So if it's equal to zero, then the next one, which is down, is negative one, negative two, and positive two. So 3p6 is positive two. Do you understand the pattern, guys? Okay, I'm gonna do another example here. 3p4. Now, now count with me. One, positive two, positive one, zero, negative one. So the answer for 3p4, if it's 3p4, its ml would be the ml would be ne ml is equal to negative one. That's how you find the ml. But how about the ms? Okay, so the ms can be either be this. It can either be negative 1 over 2 or positive 1 over 2. But how do we know if it's negative or positive? Whenever the arrow is going up, that's a positive 1 over 2. If the arrow is going down, it's a negative 1 over 2. So, what happens here is that whatever it lands on last, for example, this is okay, I'm going back here. We have to find the ms of this, the magnetic spin. So, it's equal to 4, right? It's 4. We stop at the fourth count. One, two, three, 4. And what's 4? It's down. So if it's down, it's negative 1 over 2. Now let's try 3p3. 3p3, right? This one here, 3p3. 1, 2, 3. And what does 3 do? It's up. So therefore, it's 1 over 2. So that's how you find the quantum numbers, and that's how you find the electronic configuration. I think that's literally everything. If you have any questions, just ask me.